All right. Good evening, everyone. Thanks for joining for today's session. So, today is the third problem solving session for the course numerical methods. And I think around two people are already here. More people will join probably soon. And today we are going to talk about week 3 lectures. And the week 3 almost covers about like the entire week 3 covers about eigenvalues and eigenvectors, how to find them, how to numerically calculate them for any matrix, given matrix, n cross n matrix, right? So for a given n cross n matrix, how do you find eigenvalues and eigenvectors, and what are the different theorems and what are the different methods, both iterative and the direct method. uh, okay. So that's what we studied. Maybe we will quickly take a look at about these eigenvalues and eigenvectors. So we all know, I mean, most probably everyone must have known what is eigenvalues and eigenvectors, and also you know how to find them. So basically, eigenvectors is like a special vectors along which the if you consider A as a transformation matrix, eigenvectors is a special directions along which the values just scale, and the scaling factor is called the eigenvalues. And if you want to find out how to, if you want to, for a given matrix, if you want to find out what are eigenvalues and eigenvectors, you probably write it like something like this. You take a determinant of A minus lambda I, where lambda is the eigenvalues, and that will give you a characteristic polynomial. And uh, if you take the roots of that polynomial, that will be your eigenvalues. And once you find eigenvalues, you put that in Ax equal to lambda x expression, and then or you know, A minus lambda I x expression, then you will be able to find out x, where the x vectors are the eigenvectors. So as I said, if you consider A as a transformation matrix, then eigenvectors is along the direction where the vector just scales rather than changing the direction. Okay, and there are two multiplicity that we saw: algebraic multiplicity and geometric multiplicity. Algebraic multiplicity corresponds to maybe let me quickly check my recordings. Okay, algebraic multiplicity corresponds to number of times a uh, characteristic value repeats, right? um, Number of times the characteristic value repeats, or the root of the characteristic polynomial repeats, right? But in geometric multiplicity, for a given lambda, how many linearly independent eigenvectors are present is the geometric multiplicity. And usually geometric multiplicity will be less than or equal to algebraic multiplicity for that eigenvalue. Okay, and that's what we expressed it. So in, to be precise, it is going to follow if m is the geometric multiplicity of that eigenvalue and n is the algebraic multiplicity of that eigenvalue, then m you can find out to be n minus rank of A minus lambda I, where lambda is the corresponding eigenvalue. Okay, and there are few more um, properties of eigenvalues that we saw. I think most probably you might have already studied in linear algebra course, so I'm not going to repeat here. And then finally, we also studied something called diagonalization. So when you have n, if it is an n cross n matrix, and if you have n linearly independent eigenvectors, linearly independent in the sense that each vector, let's say you have n vectors, you cannot write one of the vector in terms of other n vectors. Okay, so in this case, let's say if I want to write, if let's say 1 0 and 0 1 are your eigenvector. Okay, sorry, I think I should have 1 0 and 0 1 are your eigenvector. So you cannot write 1 0 in terms of 0 1 basically. Or let's say, if let's say this is the let's say this is a vector, and this vector you can write it as 1 0 plus 0 1. So in this case, 1, 0 and 0, 1 are linearly independent eigenvectors. However, 1, 1 is a linearly dependent linearly dependent vector, which depends on both 1, 0 and 0, 1. Okay, so if in your eigenvectors, every vector should be linearly independent of each other, which means you cannot represent one of the eigenvector in terms of other eigenvectors. That's what linearly independent means. Now, if you have a linearly independent eigenvectors, I mean, you for a given matrix, you find the eigenvalues and eigenvectors and make sure that if it is linearly independent, then that matrix is called diagonalizable. And the diagonalizable in the sense you can just represent a matrix in terms of eigenvector and eigenvalue matrices, where P is eigenvector, P inverse is eigenvector matrix inverse, and D is the eigenvalue. It's a diagonal matrix with eigenvalues populated in the diagonal elements of your matrix. So this gives us an advantage. So if we want to find out a square or a power 4, then you just need to multiply. You just need to square the eigenvalues and then multiply their respective eigenvector matrices together. So this significantly simplifies your computation. So and then we studied about similarity transformation. And similarity transformation, here we said A and PAP, P inverse AP are similar, and the transformation A to P inverse AP is the similarity transformation. So basically we are telling that uh, uh, we multiplied P inverse matrix to AX equal to lambda X, and these both will have same eigenvalues basically. Okay, so both A and P inverse AP will have same eigenvalues, and such a transformation is called similarity transformation. So this, of course, we saw this how it is useful in let's say like in Jacobi method. So that is also a similarity transformation, and that is so in the Jacobi method we preserve the eigenvalues and eigenvectors while doing this transformation. So it's a similarity transformation. Similarity in the sense eigenvalues does not change. Okay, now this reduces the complexity, evaluating the eigenvalues, all this we all know. And then there are a few additional things that we need to take off in terms of similarity transformation. So basically every Hermitian matrix, which we write it as A equal to A transpose conjugate. So here A is a complex matrix. Till now we all usually see only real matrix, but A matrix can be complex too. So it can be with complex numbers. So if that is the case, then is unitary, similar to a diagonal real matrix, and A is normal if and only if the unitary is similar to the diagonal matrix. All right, so these are normal properties of things, doesn't matter. So and then we saw something called Jordan canonical form. This is useful for us to understand uh, whether the matrix is diagonalizable or not. If you get a if you can find a diagonal matrix, then in the sense the Jordan blocks are equal to the number of Jordan blocks are equal to the number of eigenvalues, then it is a diagonalizable matrix. So this is also one of the way that you can find out where the Jordan, based on the Jordan canonical form, whether the matrix is diagonalizable or not. So A is diagonalizable if and only if the size of the Jordan matrix is Jordan blocks is 1, which means like for each and every eigenvalue, the size of Jordan block is 1. So sometimes here, when you have like 3 repeating eigenvalues, then and also you will have only 2, let's say you will have like 2 independent eigenvectors, right? Then you will end up having a Jordan block whose size is greater than 1, right? Then this matrix will not be diagonalizable, and it's also called a defective matrix. Okay, and then we also saw singular value decomposition. So this is if you have a rectangular matrix, not a square matrix, then you do singular value decomposition. So These becomes helpful when you have a when you want to invert a rectangular matrix. So you're trying to write A in terms of U, S, and V. Now, if you want to invert A inverse, A inverse cannot be found for a square matrix. Instead, you find U, S, and V, and whatever the operation that follows, you replace that with U, S, and V. Okay, so this will be useful in terms of mechanics, in mostly in robotics, trying to find out. Uh, you know the dynamics of robo motion when you want to convert uh, the joint space to task space, and those places you will use this singular value decomposition. So most of the time your robo will have like multiple degrees of freedom, and the multiple ways it can move. In real space you have only three directions, but the robo can have more than 3 degrees of freedom, like rotation, linear motion, and things like that. So at that time you will have a matrix which is not square, and when you want to do similar analysis, let's say equation of motion you are writing for your robo, and then you're trying to invert it and trying to find out what should be the force and velocity that you're trying to give, at that time you will have to invert the transformation matrix, and that matrix will not be square. That time it will be rectangular. At that on in those places you will replace the A matrix in terms of U, S, and V, and it simplifies your calculation later. So and then we saw something called Greshgorn's theorem. In Greshgorn's theorem, you have you can just inspect the matrix and you can see whether you can find the eigenvalue or not, or you can just identify what is the space in which my eigenvalue is going to uh, in which the eigenvalue is going to be present. So what we do is, we for a given matrix we sum up the all the off diagonal elements on that row, and then uh, you plot something called Grishkorin disk, and you draw it for every row. In that way you will be able to find out multiple disks like this, something like this, and the union of all these disks is somewhere inside this union your eigenvalue is going to lie. So that is the Grishkorin's theorem, and we all saw the proofs and things like that. And one place where this is going to be useful is for preconditioning the system. Usually you end up in yield condition system. We also saw how to find out the condition number, right? So similarly, at some places when you try to solve a system of linear equation, your matrix A matrix will become yield conditioned. Your condition number will be very large. So in order to solve it as accurate as possible, you try to precondition the system with this preconditioning matrix. So basically you multiply a matrix to A and on both sides. So whatever the solution is going to give will still remain same. So it is not going to be varying. But the choice of P should be in such a way that the whole condition of PA, condition number of PA is less, so that your round of errors will not exceed. So to find out that, then those places the Grishkorin's circle things will be useful, and it's also useful in multiple places. It's just one of the application. So finally we saw, okay, all these things are fine. We want to find out eigenvalues and eigenvectors, and if that is the case, how do we do it? First we saw for symmetric matrices. If a matrix is symmetric and if I want to find eigenvalue and eigenvector, then the method is Jacobi method, the easiest method, where you do series of rotational transformation, but rotational matrix itself will change your eigenvalue, but the rotational transformation here is a similarity transformation. That's why it preserves the eigenvalues and eigenvectors of your matrix. Okay, so it is an iterative method to determine eigenvalues and eigenvectors. And the rotation, when you do rotation, the rotation angle you should choose. The rotation angle is based on this algorithm. Okay, we all saw how the proof is, and if you are interested in the proof, please I mean you guys must have attended the classes, so professor was explaining that, so I urge you to take a look at it. Here I'm just going to brief the methodology how to solve. So first thing is we find the largest off diagonal element, and based on that we select that P and Q row and column, and once you find out, you find the rotation angle based on this, or based on this big formulas. So there are two ways, either way is fine. And sometimes tan inverse is not available in your let's say when you're trying to solve it. Um, you can easily do multiplication, subtractions, additions and division, but finding a tan inverse requires a multiple it requires a different logic. It is not as simple as multiplications and divisions. So that's why tan inverse may not be that accurate based on the system that you solve or based on the computer that you have. So to avoid that, people take a different route. So first you find tan theta based on this, and then or this, and then based on tan theta you find sin theta and cos theta. In that way you no need to invert the tan. Okay. So but since we know tan inverse, and if it is simple it's going to be 1 0.5, then you can easily find out the angle. So while we solve by hand, we go with this. But when you're programming or when you're using it in a software, then you have to go with this logic. Okay. um, and then so once you find the angle, you need to construct the rotation matrix. And once you find the rotation matrix, so the rotation matrix, we all know it's going to be cos minus sine and cos. These are the four elements that you have within the rotation matrix. Now you need to place these four elements at a appropriate place. So once you place that, that becomes your overall rotation matrix. So once you find that matrix, then you multiply J transpose AJ, and that will, so this is a similarity transformation. Once you do this transformation, then you get A1, which is a transformed matrix, and you repeat it until all the off diagonal elements become 0. So basically all the off diagonal elements, if it becomes 0, then your diagonal element is going to be your eigenvalue. So that's the logic. So finally we are trying to reduce it down to the just the diagonal matrix which contains eigenvalues. And the multiplication of all these j's, the transformation vectors, is going to be your eigenvector matrix, in which each vector is going to be your eigenvector for the corresponding eigenvalue. Okay. So that is how we do it, but it requires a lot of matrix multiplication, and if the n becomes very large, hundreds and thousands, it becomes very very difficult. Like you need to keep on repeating this uh, for multiple times to eliminate all the off diagonal elements in order to arrive at one eigenvalue, right? Or the overall eigenvalues. So that is the drawbacks of this. And so, and next one we saw is power method. In power method, uh, usually it finds out only the dominant eigenvalue, and it is also important that you have one single dominant eigenvalue. If not, this is not going to work. And also n linearly independent eigenvectors. So these two conditions has to be satisfied in order for this power method to work. And it is much simpler. You just start with an initial vector, initial guess vector, and then you start multiplying to the a, the whatever the vector you get, and you find the largest element in that vector. You normalize the entire vector with that, and that largest element you assume it as current eigenvalue, like the iterations eigenvalue, and you keep repeating this again and again until the successive eigenvalues become same. So and so proceeding forward in any more iterations will not improve your eigenvalues. So that will be your eigenvalue, and the corresponding vector that you find v will be your eigenvector. Okay. So it's a much simpler, but it has certain conditions that needs to be satisfied before you apply it. Now this will give you one eigenvalue and one eigenvector. So now you want to find let's say the next eigenvalue, then you use something called method of deflation. Basically we are tricking the matrix and we are trying to make that matrix, make one of the eigenvalue of that matrix to be 0, so that the next dominant eigenvalue will be, you can use the power method to find next dominant eigenvalue. So that is how we do it. So basically we find another matrix which is your original matrix, and minus the lambda 1 u transpose, where u is v1 by modulus of v1. Now this lambda 1 is the dominant eigenvalue you just found using the power method. Once you find this, you subtract it with this matrix, then the matrix will have eigenvalues to be 0, lambda 1, lambda 2, and lambda n. Basically the lambda 1 becomes 0. So the dominant eigenvalue for this matrix is going to be lambda 2, right? And you apply power method, you find lambda 2. And once you find lambda 2, you take a1 minus lambda 2 u transpose you do, and then you apply power method again to find lambda 3, and you keep doing it until you find lambda n. Okay, this is one way, and it also has some disadvantages. Basically the convergence rate depends upon the most dominant and the next dominant eigenvalue, right? If the distance is too large, then it is going to be converge faster. If the distance is small, it's going to be taking a lot of time to converge, or lot of iterations to converge. And the next one is shifted power method. So basically we have this will give you only dominant eigenvalue, the power method. Now if I want to find an eigenvalue which is close to, let's say, these numbers, let's say I want to find if there is any eigenvalue exists, let's say I want to find out eigenvalue in between 0 and 10, if there is any eigenvalue exists. So you start with, let's say, 5, and then you start doing this iteration, and at some point it will converge to some value, and that will tell you that, okay, this is the nearest eigenvalue that you can find out, and the corresponding eigenvector will be the that will be the corresponding eigenvector. So for that you use these properties. So basically you now write the iteration function to be yk plus 1 equal to a minus lambda I, where alpha I, where alpha is the initial initial guess value that you take. Okay, so and you can see here it is an inverse. So either you can find the inverse, but finding inverse is costly when you are going like 100 cross 100 matrix, or 1000 cross 1000 matrix. Now so what people usually do is they take this to this side, or basically they multiply a minus lambda I inverse on both sides, or just a, then this becomes identity. So this will become what do you call a system of linear equations, which we saw in the first week. You can use Gauss elimination, Gauss Jacobi, Gauss Seidel, whatever method you want to solve that system to get yk. Okay, so either you can find inverse, so because you are given only a, right, and alpha, so you need to find inverse here. So instead of finding inverse, you cast it as a system of equations, linear equations, then you solve them to get y. So once you get y, same method, like you find the maximum element, you divide them, you basically normalize them, and you end up having the new vector k, and you again go back, multiply it with this, and then keep doing until convergence. Okay, and either you can keep the alpha to be same from first, or you can keep changing it based on this, or you can also use with Rayleigh coefficient, which is going to improve your convergence. Basically you update alpha k in this manner. Okay, these are the different ways that you can change your convergence rate. The other one is inverse power method. So basically in power method we find dominant eigenvalue. In inverse power method you can find smallest eigenvalue by using this property of the eigenvalue, right? So now the same thing, if dominant eigenvalue of a is lambda, then a inverse is going to be the eigenvalue of the a inverse is going to be 1 by lambda. So that is going to be your smallest eigenvalue. So you do it in a reverse. If I seek for smallest eigenvalue in a, then a inverse is dominant eigenvalue is going to be the smallest eigenvalue of A. So that's why you replace this A Vk into A inverse Vk. So this A inverse, or you can just write it like B is equal to A inverse, whose this dominant is the smallest eigenvalue for A, just A. Okay. So in that way you do are basically same as the previous one, shifted inverse method, and you find the vector, you keep iterating again and again until you reach convergence. And important, I don't know whether you guys observe this. So in this case what you will have is uh, so instead of finding the inverse A inverse, usual what you can do is, as I said, you can take A inverse on the other side and you can write it like this, and we want Y, so you can write either like A B as a augmented matrix and do what other things are there, like Gauss elimination, Gauss Jacobi, Gauss Seidel, or whatever you want to do, you can do. But in this case, if you see, for every iteration that you do, this A does not change, right? So since A does not change, uh, here is where you can use LU decomposition. So you take A, you do LU decomposition, find L and U, and that is not going to change for each and every iteration. So that's all. Once you find L and U, then your problem becomes simpler. You just multiply, you do forward elimination, backward substitution, forward elimination, backward substitution, and forward substitution, backward substitution, and keep doing this multiple times for each and every iteration. That will help you in reducing the computational time. So this is for like a 100 cross 100 matrix, when you, let's say when you are creating a solver which needs to find out eigenvalues, right? In those places you do this. All right, so that is where we stopped. We found like Gauss Jacobi inverse method and variance, there's no Gauss here, the Jacobi's method, uh, power method, and its variant, such as like inverse power method and shifted inverse power method, and also with Rayleigh coefficient and things like that we saw. These are the methods to uh, find out eigenvalues and eigenvectors. Yeah. All right, so this is what we saw in this week's lecture. If you have any questions, I will be able to answer. If not, we will go forward and solve a couple of questions. Like I have only 2 questions, and I saw that your assignment wants you to solve Jacobi method and power method, right? I think one power method and one inverse power method. So I thought I will solve one of them, and it will be useful for you to yeah, solve the assignments. So if you have any questions, please let me know. Yes, please go ahead. You don't need to raise hand. You can just stop me in between. There's no problem.
Hello, sir.
Yes. Which PDF?
This session PDF of problem solving.
Yeah. So every session's PDF will be shared in the same Google Sheets page that same Google Drive link, which is present in that Google Sheet.
Okay, sir.
So you will be able to access it from your NPTEL portal. Okay.
Okay, sir.
Yeah. So once the session is over, that I will upload the notes. All right. If there are no questions, let's just go forward and solve a question here. So first thing is to use Jacobi method and to find eigenvalues and eigenvectors. And I took a simple problem here, and I hope it's also simple in the assignment. So as I said, the Jacobi method is only for symmetric matrix. First, you need to check whether the matrix is symmetric or not. So symmetric matrix in the sense you have a, or basically aij is aji, right? So in this case 0 a12 and a21 are same, 0 0, and a31 and a13 are same, yeah, which is 1, similarly 0, and you have a diagonal element which is 5 minus 2 1 5. Okay, so this is a symmetric matrix, so you can apply the Jacobi method. Now what is the step 1? So if I go back to this notes, and I encourage everyone to take notes, I mean not the this notes will be available, but the notes of while you were listening to the lectures, I encourage you to take notes, so it will help you remember what is going on. So here the iteratum, the first thing is to find largest off diagonal element. Let's do that. So the first step 1 is to find largest off diagonal element. So what is the largest off diagonal element here? So this is not a diagonal element, so it is a off diagonal element. So which means you can check here. So 5 is the largest, but it is not a off diagonal. So the off diagonal elements are these and these. So in which one is the off diagonal, largest off diagonal element. So basically I can say a13 equal to a31 is equal to 1. So this is your largest off diagonal element, which means p is 1 and q is 3. So p is row and q is column. Okay, this is the first row and third column. So p is 1, q is 3. So the second step is to find the rotation angle. Rotation angle. So to find rotational angle, we have a equation which is theta equal to tan inverse of what is it? A p 2 times of 2 times a p q divided by a p a q q minus a p p. Now you just need to substitute here. So p and q are 1 and 3. So let's say if I want to write it explicitly to make you understand, it's going to be 2a13 divided by a33 minus a11. Okay, now theta is going to be of tan inverse of 2 times a13 is just 2 and a33 is 1, and sorry, a33 is 5, a33 is 5 and a11 is 5, so it's going to be 5 minus 5, which is 0. So if you want to write this is going to be 2 by 0, and we all know this is going to be tan inverse of infinity. So infinity happens only if it is at pi by 2, right? Tan 90 degree is infinite. So if that is the case, then this is going to be theta equal to half into pi by 2, which is equal to pi by 4. So this is your rotation angle. Okay. Now the next step is to find orthogonal matrix. Orthogonal. Sorry, it's not orthogonal matrix. Yeah, I mean it is an orthogonal matrix, but it is also called rotational matrix. So the rotational matrix is going to be J, and again of course it is going to be 3 cross 3, but where you have to place it, that's the question, right? So you take a look here. This is our rotation matrix, and you found p and q. P is 1 and q is 3. So this has to be at first row. So this has to be at 1 comma 1. Okay, and this has to be at 3 comma 1 comma 3. Okay, and this has to be at, so this is 1, this is 3, and this is 1, and this is 3, right? 1 3 1 3. So this becomes 1 1, this becomes 1 3, this becomes 3 1, and this becomes 3 3. Okay, so this is row, I mean these two is row and these two is column. So this is how you place them. You may need to remember this, but it is simple, like um, so how do I put it? So we know it's 2 cross through rotational matrix, and you can just correlate it with P and Q like this. All right. So as I said, it's going to be cos theta and minus sine theta 1 3, and 3 1 is again sine theta, and this is cos theta. So once you put this, the diagonal elements will be 1 and all the off diagonal element will be 0. That is how you fill this matrix. Okay, let's go forward. Now theta is pi by 4, so let's say I will just replace this with pi by 4, pi by 4 cos pi by 4 sin pi by 4, pi by 4 cos pi by 4. So basically we are rotating it 45 degrees, right? Now what we have to do, we need to find out, the fourth step is to find transform matrix. Here it is a similarity transformation. If you multiply it once, it rotates 45 degree. But what you also do is you multiply it with J transpose. So it rotates back again to 45 degrees. Transformation matrix. So usually if you just multiply with rotation matrix, your eigenvalues will change. Okay, but this is in similarity transformation. So that's why you do J A J transpose, or J transpose A J. All right. So this we are denoting it as 1, which means this is the first iteration, and the next iteration will be A2 J transpose A1 J. Okay, and maybe I will also denote this as 1, so that J1A J1. All right. So what is this going to be? Cos pi by 4, I think it's 1 by root 2. 0. Sin pi by 4 is 1 by root 2, but there is a minus, so minus 1 by root 2. 0 1 0. Sin pi by 4 1 by root 2. 0 1 by root 2. Okay, this is your rotation matrix. Now let's just substitute it here. It's going to be 1 by root 2 0 1 by root 2 0 1 0 minus 1 by root 2 0 1 by root 2, and then there is a 5 0 1 0 minus 2 0 1 0 5, 5 0 1 0 minus 2 0, right, and 1 0 5. This is going to be J0 minus 1 by root 2 0 1 0 1 by root 2 0 1 by root 2. Okay, so let's multiply these two first. Let me just keep this here. 1 by root 2 0 1 by root 2 0 1 0 minus 1 by root 2 0 1 by root 2. How this is going to be 5 by root 2 plus 1 by root 2, which is 6 by root 2, and then this is going to be 0, this is going to be minus 5 by root 2 plus 1 by root 2, so it's going to be minus 4 by root 2, and This is going to be 0. This is going to be minus 2. This is going to be again 0. This is going to be 1 plus 5, which is 6 by root 2. If I make any mistakes, please let me know. And this is going to be 0 again. Sorry. 0 again. And this is going to be minus 1 plus 5, so 4 by root 2. Okay. All right. Now let's multiply these two. So what is these two going to be? So 1 by root 2 times 6 by root 2 is 6 by 2. And yeah, 6 by 2 plus 6 by 2. And this is going to be 0. This is going to be minus 4 by 2 plus 4 by 2. And this is 0. And this is minus 2. This is again 0. And this is minus 6 by 2 plus 6 by 2, so that is going to be 0, and this is 0, and this is 4 by 2 plus 4 by 2. So this is also going to be 0. I'm just replacing it here. This is also going to be 0, and this is 6 by 2 plus 6 by 2 is 6, and 4 by 2 plus 4 by 2 is 4. This is your A1, and what you got is you already got an diagonal matrix, so which means the eigenvalues are 6, minus 2 and 4. So sometimes you may not end up with first iteration itself. You may need to do 1 or 2 iterations. In this case, what happened was, if you look at this matrix, you already have off diagonal elements. Some of the off diagonal elements 0, so you no need to repeat them. So let's say, for example, if you have 1 1 1 1 here, okay, then or 2, let's say you have, then you need to first eliminate these off diagonal elements, then you have to move forward, and you would have came up to this stage. So that is the difference. Here we already have, so I took a simplified problem so that I can finish it in time today. Anyway, this is how you find the eigenvalues. Now the eigenvector is simple. What you have to do is this J matrix is your eigenvector, where we already found the J matrix. It's 1 by root 2, 0, 1 by root 2, 0, 1, 0, minus 1 by root 2, 0, 1 by root 2. So basically, this one corresponds to lambda equal to 6, and this one corresponds to lambda equal to minus 2, and this one corresponds to lambda equal to 4. Okay, these are the eigenvectors. That's all. So once you find, if this is not the case, if you are doing a lot of iteration, then it's going to be just J1 multiplied by J2 multiplied by J3. Okay, that is how you find the entire eigen vector matrix. All right, any questions?
Hello, sir. Good evening, sir.
Yes, please go ahead.
Sir, actually, in power method, I have one doubt.
Okay.
We are taking the initial eigenvector as sometimes 100 or 111. So if we take 100, the iteration will be finished yearly. I think short number of iterations. If you take 111, more number of iteration is going. Is it right concept, or is there any shortcut for that?
So there is no way we can say that. So whether it might be possible that 111 might work or 100 might work. So there is no way. It's just an initial guess. We don't know it yet. So if it is close to,
We can take any. We
you
can
can
take
take,
any.
correct. We can take anything, and only if we do, we will know whether
Uh,
it is a, whether it is best guess or whether it's not a not so good guess.
no. I'm asking for only time saving. That's what.
Yeah, time saving, we don't know that. That is the thing.
Oh, there is no
There
shortcut
is
like.
no rule that 100 will work or 111 will work. It's just
Okay,
an
okay. That's
initial
what
guess
I'm.
value. Yeah, yeah. There is no shortcut in that.
Okay, thank you.
Okay,
Thank you, sir.
sure.
Okay.
Sometimes maybe when you solve a lot of problems, then uh, sometimes when you look at the matrix, you will be able to guess. Uh, but I'm not very aware of. You might be able to guess which would be the best solution to start with. So uh, there will be some studies about which should be your first initial guess in order to solve such a thing. um, but I'm not really aware of this. And as far as my understanding, this is the case. Even whenever you have an iteration, whenever you are trying to take a guess value, uh, you have to, only if you do it you will know. So same like Newton-Raphson. In Newton-Raphson you can take three. So let's say your root is 3, you can take from 10 and you can arrive at the same place, or you can take 4 and arrive at the same place much quicker manner. So similarly, all these things can happen. But there are some advanced studies where people might have done how to take a best initial guess, but not for for 3 cross 3 matrix or for solving your assignment problems. Not for that, but for much bigger matrix, something like 100 cross 100, 1000 cross 1000 matrix. At that time, it is usually a good idea to start with the best guess value. So people have done advanced studies in that, uh, but not for solving these cases. Yeah. All right. Good question. Anything else? All right. So I'm assuming that there are no questions. Jacobi method is easy. And please remember, this is only for symmetric matrix. If you want to go for like more general matrix, if you want to find eigenvalues and eigenvectors for that, then you have to use power method. And also for power method, you should have n linearly independent eigenvectors. Only if that matrix does have n linearly independent eigenvectors, then power method will work. If not, it will not work. But we don't know for sure beforehand that whether the matrix has linearly independent eigenvectors or not. So there's only way to find out is apply a power method and see whether it works or not. And once you get eigenvalue and eigenvector, you always have the condition ax equal to lambda x condition. You put in that condition, and then that will give you whether it is a proper eigenvalue and eigenvector or not, or it has converged to some wrong value, right? So that is the way that we usually find out. All right. Um, since there are no questions, I'm going to move forward with power method. So use the power method to find the dominant eigenvalue here. Okay. Here again, I have a 3 cross 3 matrix, and these are the this is the A matrix. Now, what is the first step we do in power method is is to choose a vector. Okay. So first thing is we will take an initial guess value of vector. And one more thing about this vector is this vector cannot be an eigenvector for some other eigenvalue. So if even if that happens, then this method will not converge. So that is also one of the problem. But we don't know for sure whether the eigenvector is eigenvector of, whether the vector that we take initially is an eigenvector for this matrix or is it a eigenvector for some other eigenvalue in the same matrix? We don't know that. So we just have to do a trial and error methodology. So first thing is we select V naught. Let's say we select it to be 1, 1, and 1. Okay. Or if you want to select a different, I can also select different. That's not a big problem. We will go with 1, 1, 1. Maybe you guys try with 1, 0, 1 and see whether how that behaves. Okay. So now the initial guess is 1, 1, 1. So what is our next thing? So next thing is we want to find the iteration. Let's say iteration 1, iteration number 1. So y1 is going to be a times v0, which is going to be minus 15. Okay, I don't want to write this matrix again and again. Just copy paste this. Okay, so this is the matrix and 1, 1, 1. So if you multiply them, it's going to be 15 minus 4 plus 3, and correct. Check. Okay, I think this is minus 3 and minus 3, minus 12, 6. Okay, there's a small changes in the value. So it's going to be 15 minus 4 minus 3, so that is 8, and minus 10 plus 12 minus 6, I think that is minus 4, and minus 20 plus 4 minus 2 is minus 18. Okay, and the maximum of this vector is minus 18. So if you take minus 18 out, let me write it down here. Y of 1 is equal to, if you take minus 18 out, then it's going to be 8 by minus 18 minus 4 by minus 18, and then this is going to be 1 minus 18 times minus 0 0.444, 0 0.222, this is 1. Okay, now the second iteration is going to be, so basically what I'm trying to do is I'm just took 18 because that is the maximum value. So that's the one of the rule, right? So if you go back, we find the maximum largest element. Where is it? We find the maximum largest element and then we divided them equal to xjk. Okay, this is a minus 18, and so we divided it, and then it becomes this. Similarly, we go for second iteration. It's going to be y of 2 is equal to a times v of 1. So what is v of 1? We didn't write that v of 1. So basically the v of 1 is going to be this one, and this is our, let's say, lambda of 1. Okay, now again you multiply the matrix. You just need to repeat this again and again. It's just, it involves a lot of multiplication. Let's try to do it. This is minus 0 0.444, 0.2221. Okay, and this will give you so it's 15 times 0.444. If you guys have done it, please let me know. Into minus 1 minus 4 into 0 0.222 minus 3. This is minus 10.548. Similarly, this is 4.444 plus 12 into 0.222 minus 6. This is 1.108 and minus 20. 20 times 0.444, 4 into 0.222 minus 2. This is 7.768. So again, what we have to do, we have to take the maximum element outside. So here the maximum element is 10.548. So if I take that out, minus 10.548, or basically I'm just normalizing the vector based on 10.548, assuming that at this iteration my eigenvalue is 10.548. So this is going to be 1.108 divided by 10.548 is 0.105, and 7.768 divided by 10.548 is 0.736. Okay, I think there should be minus sign here and here because you are dividing it by 10.548. All right, now this is your v of 2. Okay, so now you go to third iteration. So from first iteration, from minus 18 it has reduced to minus 10.548, so it has clearly not converged. So let's go to third iteration. So y of 3 is a times v of 2 a times 0.105 0.736. Okay, so what is this going to be? Okay, this is going to take a lot of time. What I will do is I will use some advanced calculator that I have. So so our vector is minus 1 0.15 0.736. Now if I do this again, I am going to get vector to be 0.93. Okay, I'm just writing here the final answer. This is going to be minus 18.95 times 0.93 minus 0.36 minus 1 minus 0.361 and minus 1. Minus 1 or 1? Yeah, minus 1. Let me check again. Minus 20 plus 4 into minus 0.105 minus 2 into 0.736 divided by 18.95 minus 20 minus 4 into minus 0.105 minus 2 into 0.736 divided by 18.95. Sorry, it's plus. Okay. All right, and this is also plus minus. Okay, we can keep repeating this again and again. This is fourth iteration. Let me just write down all the results so that it is easy. Or maybe I will also show you guys how to do it in MATLAB, time permits. So the fourth iteration becomes a times v3, right? y4 is a times v3, which is 18.394 times 1 divided by 0.415 minus 0.981. Okay, and the fifth iteration becomes y of 5 equal to av of 4, which is minus 19.698 minus 0.995, 0.462, and 1. Okay, similarly you can keep doing is y of 6 is a times v5, which is minus 19.773, 0.48 minus 0.999. Okay, then y of 7 is a times v7 minus 19.956, 773, okay, 922 minus 0.997. Please check this calculation. I did it by myself, but there's a possibility that there might be some mistakes. I don't know. And then 7 minus 19.956, 0.495 minus 0.999. Okay, and finally y9, which is av8, which is 19.956 minus 1, 0.495, 0.999. Okay, sorry, this one minus. So you can see that 8th iteration and 9th iteration is, gives you the same result, or it is not it is changing in the 4th decimal, but at least up till 3rd decimal you do not have any change, which means this is your eigenvalue. So what is your eigenvalue? Your eigenvalue is somewhere around 19.956, and the corresponding eigenvector x is 0.495 and minus 0.999. Or in other words, let's say if you, since these are all real numbers, we expect it also to be real numbers. Probably it will be like eigenvalue is 20 and the corresponding x is 1.5 and minus 1. Okay, so this is at infinite iteration, in technical sense. If you do a larger number of iterations, then you will be able to reach 20. Okay, and 20 is one of the dominant eigenvalue for this matrix. Okay, this is how you do you use power method to find dominant eigenvalue. Is there any questions till now?
Sir, I have a doubt in that.
Sure, sure.
The eigenvalue is minus 19.956, but you were telling that plus 19.956. Is
Right,
that
right, right.
okay, sir?
See, yeah, okay. Yeah, it's a good confusion to have. So what we have is a times v. V is what x we are telling, right? So a times v is equal to some minus some, let's say, some constant c times v. Okay, but ideally how do we write this? Av plus cv equal to 0, and a sorry, a minus cv, and what do you write? A times ci v equal to 0, and V is your eigenvector and C is your eigenvalue, correct?
Oh,
So
okay, sir.
wait, yeah, I mean you're right. One second, I think I got confused. So if that is the case, what will happen? uh, so which means if I take C to be minus 19.956, this is Ax equal to lambda x. um, yeah, very good question. I didn't realize this.
Thank you, sir.
Ax equal to lambda x. So what we wrote is A times this x we are taking is 1 point, no, what is it, 1 0.5 minus 1, 1.5 minus 1. This is what we got at the final iteration, and this is equal to, I'm telling it is going to be minus 20 times 1.5 minus 1. Okay, so if this is the case, yeah, you're right. This, if this is eigenvalue lambda is minus 20, then your eigenvector is this one. But whether eigenvalue is plus 20 or minus 20, so let's just substitute it in the, so what is A? 1.5 minus 1 equal to 15 minus 2 plus 3, which is 16, and then correct, right? Okay, 15 minus 2 plus 3 is 16. 10 minus 10 plus 6 plus 6, and then minus 20 plus 2 plus 2, right? So this is going to be, sorry, 6 plus 6 is 12, 12 minus 2 is, this is going to be 2, and this is going to be minus 16. So what this gives, can I write it in terms of, if I take 16 out, then 1, 2 by 16 and minus 1. This and this is not equal. Okay. Now let's do the other way. Minus 1 minus 0.5 plus 1. Correct? Is that what we have? 1 second. 1.5 minus 5. 1.5 minus 1. 1.5 minus 1 So if I change it, minus 15 plus 2 minus 3, so it'll be minus 16. Then minus 6 minus 6, it will be minus 2. 20 minus 2 minus 2, this will be again 16. I think I have missed something here. Did I write these numbers right? Whether I take 20 or minus 20, none of them is matching. 1 second. Just give me a minute. Let me turn back to my advanced calculator. So this is giving 1 minus 0.5 minus 1. One minus 0.5 minus 1, and what I'm telling is a times x, a times v is 20 okay, what did I do? Okay, this, my brain is not working. Minus 4 into 0.5 is minus 2. Oh, minus plus 2. Okay. Okay. So 15 plus 2 plus 3. And this is minus 10. Minus 10 minus 6 plus 6. Okay. And this is minus 20 plus 2 and plus minus 20, sorry, minus 2 plus 2, minus 2 plus 2. Okay, so this comes out to be 20 minus 10 minus 20. Okay, so now if I take 20 outside, then it becomes 1 minus 0.5 minus 1, correct? So this and this are same. So this, so if I, so, but what eigenvector did we write? So we wrote 1.5 and minus 1 for 20. Okay, let's try that. So this is, so from here lambda is 20 and eigenvector 1 minus 0.5 minus 1. These are the lambda and eigenvector. Okay, now if I repeat this again, so what did we found out? 1.5 and minus 1. 1.5 and minus 1. When we do this, 15 minus 2 plus 3. Okay, this will not work. Okay, this does not work. This will give you like 16 minus 2 and whatever it is, minus 20 plus 2 minus 18 plus 2 minus 16. So this will give something like this. This will never work. 16 is 1 minus 2 by 16 and minus 1. Okay, this is not work. So this, whatever we wrote, is not right. Okay, so ideally, since, as you said, since if I'm taking 19, then this should be minus, and this should be plus. But the question is, the question still remains, how did minus 19 become 19, right? Or, how did minus 19.956 becomes 20? Positive quantity. But so till now, you guys were able to understand the problem, to understand the mistake that I made, right? So what I did was, I just wrote it to be eigenvalue 19.95, but the eigenvalue is, okay, let me tell you, the eigenvalue is, so if you do the simple logic, the eigenvalue for this is 20 minus 5 and 10. Okay, so the eigenvalue is 20, that is for sure. But only thing is, the power method, finally we end up having minus 20. But if you take the minus inside, what happens is, the eigenvalue and eigenvector falls in place. So if you take the minus inside, 20 is your eigenvalue, and the corresponding eigenvector you're able to find out, which is minus 1, minus 0.5 and 1. Okay, so until here there's no problem. So the only question, what Abhirami also have, or anyone else also I have, is, you know why not take minus 20, why to take 20? Unless I do this exercise, I will not be able to prove that. So this proves that lambda is 20, but this proves that lambda is not equal to minus 20, which means eigenvalue is not minus 20. But unless we do this exercise, we have no idea whether the converged value is right or wrong. So did I do any mistake in, is the algorithm fine? What do you guys think? So we take, so in the class notes, what did we write? CK plus 1 is, maybe I will check the, so while I check, do you guys have any other questions? It's a very good question. I didn't think about it. So what we do here is, C1, lambda 1 is C1, lambda 2, okay, and then we take C1, B1, C2, okay, all these are fine. And our iteration continues until the magnitude of the differences of the ratio are less than a given error. Power of A gives power method its name. Mk plus 1 is the largest element in Yk plus 1 magnitude. In this case, just magnitude. In this case, what did professor do? Here you got you take the whole minus 4 outside. So then you equate the whole thing in minus 4. And then third iteration, you do this minus 8.75111. Then that will give you minus 3.625, 6.125. Highest is 6.125. You take the 6.125. And then you keep doing it. The 14th iteration you will end up having 5.4773, which is the dominant eigenvalue of A. And this is the corresponding eigenvector. What is the second? Let me check. Let me change this. 3 minus 1 0 minus 2 4 minus 3 0 minus 1 1. So if I start with this, I end up having 5 4, which is what he also got, and that is the eigenvalue. And then 0.437 minus 0.233. Okay. All right. So methodology is right. But in our case, I might did something wrong. This probably should not be minus 19. It should be plus 19, which means I might have done something wrong before itself. Whatever I do, it gives the same thing. 1 minus 0.5 minus 1. Okay. One minus 0.5 minus 1. I think these are also minus. Eigenvalue is 20. Corresponding eigenvector is 1 minus 0.5 minus 1. Okay. So I think I'm a little, I might have did some mistake while doing the iteration. That might be the reason that I'm getting this. Why don't you guys also give it a try, and I will see what is the problem. So certainly the other way is, just give me a minute, I will try one more thing. Let's say if I put minus here, minus 15, minus 2, minus 3. Okay, this is going in a totally different direction. So this is 10. This is plus 6. This is minus 6. This is 20. This is plus 2. This is minus 2. So this comes out to be minus 20, 10, 20. Okay, and then this becomes 20 minus, let's say minus 20 if you take outside. Then this becomes minus 1.51. Oh, okay. Okay. So which means if lambda is minus 20, your eigenvector is minus 1.51. If your lambda is 20, then your eigenvector is different. Okay, this is the difference. It depends upon what is your eigenvector. So as you said, you are right. It can be either eigenvalue 20 or minus 20, but the eigenvector is, for this, is going to be minus 1.51. But I will anyway check, because both of them satisfy Ax equal to lambda x condition. So once you choose an eigenvalue, then the corresponding eigenvector will be coming out from here. But I'm not really sure about this number. I might have did some mistake. So maybe I will ask you guys to do it again. I will also do it and I will update it with this notes. Okay, that's a good question. I will look into it. So did you understand what I tried to do here?
Yes, sir, I can understand. One more is, suppose we are taking positive 19.956 only, getting outside means the eigenvector will be minus 1, minus 1, minus 0.5, minus 1 will be there. No,
Right.
At that case, is it possible, right?
Yeah, it is possible. So there are two values for this. That's what.
Okay, sir.
So this is also right. This is also right as per Ax equal to lambda x. Okay.
Okay, sir. Okay,
Yeah.
sir. Okay, sir. Thank you. Thank you so much.
But this is still a gray area, I admit, because whether to take 20 or minus 20, I will check. I think probably it is fine. Let me do one more. By the way, if others have any doubts, you can let me know. Let's say if I do a standard eigenvalue thing, what will happen? 15 minus lambda minus 4 minus 3 minus 10, 12 minus lambda minus 6 minus 24 minus 2 minus lambda. Determinant of this is going to be minus 15 minus lambda. It's a complicated expression. Plus 6, 4, 24 minus plus 4 into 15 minus lambda minus 2 minus lambda minus 60, then minus 3 minus 40 minus and minus plus 20 times 12 minus lambda. Okay, now if we simplify this, I don't know what lambda is going to be. Lambda probably will be 20, that is for sure. If that is the case, then only this is the right answer. This is not the right answer. But uh, I will check it and I will update with this PDF. Okay. Here are few problems you can use Jacobi method, or you know uh, inverse method you can use to find out eigenvalues and eigenvectors. Okay. All right. Please let me know what happens with this equation. And also I will check what is the criteria, what exactly there might be something that I'm missing in the method, because it will directly give you lambda and x. Okay, so I will check this and I will get back to you guys. I will update with this PDF also, and also I will update you in the next class. Okay, next week. All right, wonderful questions today. So if there are no more questions, then we will meet next week. I will be available here for another half an hour. If you have any questions, please stay back and ask. If not, we will meet next week. Thank you everyone for joining. I think almost uh, 8 to 9 people are here. Yeah, thanks for joining. We will meet next week.
Sir, can you check the second term, is that correct? Because 4 into minus 10 in minus 2 minus lambda will come, no?
4 into mm, 15 minus lambda. Are you talking about this term?
Yeah, sir.
Is minus 4. Yes.
Whether it's or
So it's a plus 4. So it's 15. Okay, this should be plus 60. No, I mean this should be minus 60 only, right? Anyway, why don't you guys do it uh, and let me know what is the lambda. I will leave it up to you guys. Thank you, Abhirami. Yes. So I will upload this as soon as I finish this one calculation. So mostly by 6 o'clock probably, or 6:30, you will be able to access this in the same drive. Is that okay, Balasanya Khadija?
Okay, sir.
All right. Thank you.
Welcome.
Thank you, Pratik. Thank you, Basanya. We will meet next week.